let's take a little look at what we mean by parameters. We touched upon this in previous episode. The parameters are the numbers that make up the model. They're actually what consist inside the GGUF file, just lots of numerical parameters, and essentially it's individual numbers that define how a model thinks and responds. You can think about it, the parameters being equivalent to neurons in a brain, and the more connections, the more neural connections the brain has, the more complex and nuanced the brain's thinking is. In a similar fashion, the more numerical parameters inside a large language model, the more nuanced and capable the thinking of the large language model is. A 70 billion parameter model is around the same ballpark as 86 billion neurons in the human brain. Okay, so that's incredibly sophisticated. And one thing I like to think about actually is you can run a human brain on an apple and a glass of water, but to run a 86 billion parameter model, you'd need significant amounts of electricity, hardware, and so forth. But that's just an interesting comparison to make, and maybe we touch upon that in a moment as well, and how we have been created and come around. But first and foremost, if we're comparing what it's useful for in terms of parameters, which is a crude measurement because you can have a large parameter model that's been trained badly, and you can have a smaller parameter model that's been trained quite well. But as a little rule of thumb, 1 to 3 billion parameter model will be good for phones, low power devices, and simple tasks. 7 billion parameter model is going to be the sweet spot for home laptops and machines. 13 billion parameter model will be good for GPU or 32 gigabytes of RAM. So we're really stepping up now. We're thinking about either a built machine or thinking about stacks. 20 billion parameters, enthusiast territory. 70 billion parameters, we're looking at an AI stack essentially to run that. So when we're seeing parameters popping up here, 5 billion params, 4 billion, down to Quen here, 9 billion. That's what we're thinking about. The amount of numerical parameters inside the large language model's GGUF file, and that those parameters are equivalent to the amount of connections inside the large language model that enables nuanced thinking to take place. And we can compare parameters to neural activity in a human brain. And the area we're going to be looking at is probably 4 billion parameters to this Quen here, 9 billion parameters, although that's a little bit of a push. So that's the kind of ballpark we're thinking about when we're just on home machinery, unless you have more capable hardware. Quants, so we see down here, let's have a look for some quant tables, and we can have an understanding of quants. Let's pop over to let's pop over to recently updated, and we put in Hugging Face. Okay, so here we go. So we've got BF, Q8, Q6, Q5, Q4. Let's pop over to here, and we've got Q2, Q3, 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 Q4, Q4. Okay, down here, there we go, F16, Q8, all the way down to Q2. What do we mean by that? First of all, what's Hugging Face? We'll have a full explainer in a little moment or two. But Hugging Face is essentially a directory where you can explore and download large language models to be used locally. So one thing to just think about is there's not many security vulnerabilities in downloading a GGUF file. It's essentially a load of numerical parameters that have been weighed. But there as we're understanding and progressing further through large language model research and, more importantly, implementation at a local level, a home level, and a commercial level, there there are things to consider, and that's why the staff pick section is really useful, not only for LM Studio but also on Olama, because it means that the large language model you are downloading onto your machinery is in fact tried and tested, and it does come from a reliable source, which is always important whenever you're downloading something from the internet. But as we can see here, Zed Hughes has got some security research, which is a GGUF parser integer overflow and division by zero. Essentially, without getting into it too much, running this GGUF file could crash or corrupt a system or a machine. It's been put up here as a security research, which is aimed to let the large language model, local large language model community, AI community, understand that there could be security flaws in certain GGUF files, and basically to take consideration to what you implement on your machine. Make sure you understand what you're running on your machinery before you run it. Use reliable sources, and to essentially move the needle forwards in improving security for large language models. So I just thought I'd touch upon that because it is important to consider. So if we just head back to looking at some of those quant values, so BF16, Q8, Q6, Q5, Q4, what does all of that mean? Well, let's head over. So quantization makes models smaller, faster, and smarter, and it supports your ability to run it on home machinery, local machinery, without needing a huge AI stack or a data center to run some of these models. Quantization is a full precision model stores every parameter as a large, highly accurate number, enormous file sizes, massive RAM requirements. Okay, so that's down here, our F16 full precision. This is like the full version, and we can see a BF16, a little bit different, but we can see that represented there. When we run quantization, it compresses those numbers down to smaller numbers, which are less precise versions. So each time quantization occurs, you lose a tiny sliver of quality, but the model becomes dramatically smaller and faster and able to run on different machinery. Okay, so if we're thinking about F16 full precision, so you need a proper stack to run this on. You can then quantize it, run a quantization process, which will take it down to Q8, Q5, Q4, Q2, and each time you run the process of quantization, it's represented in this shorthand Quants 8, Quants 5, Quants 4, Quants 2, and it's essentially telling the user, us, who is looking to download or search for a model, the amount of times the full precision model has been compressed in order to facilitate easier use on lower capacity machinery. You also have Quants. I can't remember what the I stands for now. Oh God, silly me. But essentially, I matrix. Here we go. I matrix quantization. And if we think about it, we have our F16 full precision. That's like a raw image that's been taken. We have our JPEG, which is being compressed down to support file memory when saving it to a computer or transferring it or sending it as an email. So it's nearly as good as the original, but it's just a fraction of the size. And then an iMatrix can be thought about like a smart JPEG. So it's compressed the important details more sharply than some of the lesser quality details. So if it was a picture of a human face, for example, it would compress the background behind the human more so than it would the facial features of the human in the picture, essentially. So this is what the Qs mean. It means quantization. What does quants mean? Quantization, it means compression. And how does compression support large language models? It means that we don't need the full F16, full precision large language model file, which would not be likely to run on local machinery, but instead we can compress that large language model down into a Quants 8, a Quants 5, a Quants 4, a Quants 2 compression level to run on local machinery. Okay, so the bottom line is lower quants is smaller, faster, higher quants is better quality. Okay, so choose the lowest quant compression that gives you the quality you need with the hardware you have. Okay, so quick summary when we're thinking about these models here, which one to download, available files we can see there. We're thinking about what is the most appropriate large language model. The large language model, for example, this one, Carbon, 500 million parameters, is, well, let's take this 8 billion one. So here we have, let's take this 3 billion one. So this has got 3 billion parameters. Okay, so each of these Q4, Q5, Q6, Q8, and BF16 are all the same large language model, Carbon. Okay, but they've been compressed to different sizes to support utilizing on different machinery for different purposes. So depending on what your hardware capabilities are, will most likely depend on what version of the large language model you have, and the version is a shift in quants compression size. Okay, now for LM Studio, I recommend hitting download because it arranges the, well, perhaps not with recently uploaded, but certainly if you're in the best match category, and we can look at this partial GPU offload possible tag as well to understand what the best model and download is. So for our purposes, while using LM Studio, I recommend just hitting that download. But it is important to understand what we are talking about when we see the Q5 or when we see partial GPU offload possible. Okay, so when we're talking about quants, we're talking about compression to make files more accessible for different users and to make different large language models most appropriate for different machinery. Okay. Now, earlier on, we touched upon a chocolate bar and a glass of water, or an apple and a glass of water being able to run a human brain in comparison to 70 billion parameters being the equivalent to 86 billion neurons, and how much water or power or electricity or hardware would be needed to run a human brain when you think about these large data centers and AI stacks that can only really do a fraction of human compute, at least in the most part. So that's an interesting thing to think about. We also touch upon here on compression, and if anyone knows in the audience watching what this is or this represents, yes, the answer is a fern, but what does it represent? It represents a Mandelbrot set. Each of these, oh God, I don't know what you would call it, parts of the fern, leaves, individual leaves, are made up here. So this is equal to this. What are you talking about, Joseph? You haven't explained that very well. Well, we have a lovely formula for it. Z equals Z squared plus C. This is a way of nature constantly repeating on a smaller or larger scale the same pattern. Okay. What does this have to do with quantization and compression? Well, we first of all have identified this from a man named Mandelbrot who first observed these. It's called a Mandelbrot set, and what we're looking at is a fractal. But more, and it's a mathematical equation that's found in nature, and some refer to it as the fingerprint of God left in mathematics. We have others such as pi, for example, 3.14. But why is this relevant to compression and quantization? Well, the Mandelbrot set and the idea that nature can have a finite sequence of smaller or larger items, or components or properties, for example, like a leaf. It doesn't have to be a leaf. If you take a tree line, for example, the Mandelbrot set is going to be found in the tree line, each individual branch of a tree being the sum essentially of the tree itself. And the Mandelbrot set is a simple equation repeatedly applied, which makes incredible shapes and patterns. The patterns never end, but they keep getting more detailed the more you zoom in. And they occur in plants, seashells, clouds, galaxies. Okay. The equation represents that much of nature uses this to create detailed self-similar patterns. And it's actually utilized in the mathematics of zipping up files. So when you take that huge PDF you need to send to your boss and you zip it up and send it over email because the email says we can't send the full file on its own, it's too large. Well, when you zip that file up, it actually uses the Mandelbrot equation or something similar to compress the file. So the file can be 10 times smaller, but it actually contains the same information that when it was unzipped, and then you can essentially unzip it and have all the information exactly the same. So you can take one PDF document, you can zip it up, which compresses it, quantizes it. You can send it across the internet to another machine via email. That additional user can unzip that compressed file and can extract using essentially quantization compression in reverse to restore the files back to their original state. And that is this principle of Z equals Z squared plus C, the Mandelbrot equation. So absolutely fascinating that we see not only the observations of Mandelbrot being utilized in technological advancements to this day in 2026, but also that little fingerprint of God emerges twice as we start to look closer into recreating the human mind on a technological level. And that is that, to run a human brain, you just need an apple in a glass of water, but to run a equivalency in neurons would require huge data centers the size of cities and mass water and power supply. And I really think that comparison, it really hits home and lands with me that to run one human brain, a natural brain, just is an apple and a glass of water, but to run a technological brain, it requires so much power, space, literal, not space above the atmosphere, but space in terms of I don't know what you would call it, geographical space, I suppose, space, on a 3D plane, to build these data centers, and not to mention the complexity of parts. Nvidia right now are building a co-designed stack to be able to be specialized for AI, and the amount of work that goes into that is just phenomenal. And we also see here, alongside that kind of energy comparison. We also see that we see the Mandelbrot set, a mathematical equation found in nature, left by a designer, being utilized in not only the compression of zip files that we all used to, even a kind of a layperson working in an office, but also within the artificial intelligence and large language model research and implementation as well. So absolutely fascinating. What else do we have here? Let's just nip back to our search engine. We also have, let's see if we can find one or two context window. So here we go. The small models feature 128K context window, while the medium models support 256K, K being 1000. So essentially, what is context length? When we see context length, it's how much the model can hold in its attention at once. Okay, your messages, its replies, and any system prompt all count towards this limit. Once you exceed it, the oldest content gets dropped out. So if you have, for example, a 4K context length, very, very, very small, as we can see here on that Hugging Face search, 128,000 context window, medium model 256. So if we think about 128,000 being an entire book, we can see that even a reasonable model such as Gemini 4E2B, 5.18 billion parameters, fairly new, literally released a day ago, so I will download that later. Full GPU offload possible, so it's a perfect match for my machine. We'll have a run about that. It's only yes. I won't get too distracted. As you can see, the more recent models, incredible context size. So what do we mean here? When you're kind of writing your response in, or you're providing images, screenshots to explain something, data from a Word document that you want to let the large language model understand specifically for the task that you've set it, if that context length is incredibly short, as it goes through the the input that you've provided for it, it will lose out the oldest data first. So if you think about the start of the message, perhaps, or the first file you put in, by the end file, if the context length is not large enough, it will drop out the first file that was put in, which is no use. So if we think about this, it's kind of analogous to short-term memory. A 4K context is like remembering the last few minutes of a conversation. 128K context is like having the entire meeting transcript in front of you. You can kind of draw from all of it. I think the analogy of short-term memory is not the best, because short-term memory and long-term memory and the working memory model is a little more complex in humans. But I think as a rule of thumb, it kind of brings an understanding to what we mean by context length. So keep in mind, more context is more flexibility and fewer I forgot moments, but it also means more VRAM usage and slower performance. Okay, so 4K is like a short conversation, 8 is like a longer chat, 32 is like long documents, and 128 is like an entire book. Okay, and lastly, we have model type tags and GPU tags. So if we head back over, we've got here capabilities: vision, tool use, reasoning, full GPU offload possible. If we head up to the one just above it, likely too large. If we head over to Quen, we should let's go down to one. Partial GPU offloading possible. Okay, so these are our other tags we can use to understand what model to download for our specific machinery. The model type tags: instruct, base, reasoning, code, vision, embedding. It essentially describes what the model's capabilities are. Can it accept images as inputs alongside text? That's what the vision capability demonstrates as a tag. Embedding, not used for chat, used for search and memory systems. Code, Can it write JavaScript, for example, that we're going to have a little look at in a moment or two? Reasoning, does it think step by step before answering? Is it just a raw model with no behavior? It just is pure token prediction, because essentially at the end of the day, that's what large language models do. It's predicting the next character that's going to emerge. It's not necessarily constructing the sentence, and perhaps we'd need a deeper conversation for that than today's demonstration of LM Studio. So file names often include these tags, so you know what the model can do and how it should run. So if we nip back over, that's this tool use and reasoning. So we know this model's been trained to use tools, and we know it's been trained to reason. If we pop up to one of these, we know that Google's Gemini 4e2b can receive images within its input, and it can understand them. So it's been trained on vision skills also. If we think about these GPU tags, where we've got here green, full GPU offload possible. We've got down here likely too large. We've got partial GPU offload possible. What does that mean? Well, that means full GPU offload possible means the entire model fits in the VRAM. Fastest performance. Okay, you have got the hardware capabilities to run that large language model. The partial GPU offload splits between GPU and RAM, so it's still good, but it can't be contained solely by your VRAM. So you're going to need to offload a little bit onto the GPU, essentially, the graphical processing unit, and then CPU down here only, no GPU needed. It's slower, but it might run. And what we don't have here is likely too large, which essentially means it's not a model for your system. You're going to either need to improve your hardware, you're going to need to go and get yourself a stack, or that model's designed to be running in data centers with cloud inference as opposed to locally on